vehicle batteries as energy storage for solar systems. And I think this is going to be one of those deals where it's kind of obvious to all of you, right along with me, except a couple of years from now, it's going to dawn on you how obvious it really was. This is kind of important. We're going into a battle royale with our utility grids, and it's exacerbated by a couple of exponential growth issues. One of them, of course, is the adoption of solar on the rooftop. Another one that people are a little unaware of is some of the other things going on with the use of electricity and solar in the United States. At the end of 2016, 25% of our electric usage in the United States was devoted to lighting. At the same time, about 88% of our lighting was provided by incandescent bulbs. If you go back to our first video, I talked about the migration to light-emitting diode-based lighting. That was 9 years ago. For various economic reasons, we've had very little penetration, about 12% as of 2 years ago, maybe a bit more today, and it's kind of going to go exponential here pretty soon. I bought an 8-pack of GE dimmable LED light bulbs the other day, 60-watt replacements. I think they burn 9 watts or something like that. $24.95 for 8 of them, so $3 a bulb. And so over the next 10 years, actually not even that long, it's going to go kind of hockey stick, the adoption of LED lighting. LED lighting takes about 11% or 10% of the energy of an incandescent bulb. And so our 25% of our total electricity usage in the country is going to go to 2.5% or 3%. I just bought a fixture. If you recall from our video in 2009, I said that in the lab they were demonstrating 160 lumens per watt. I just bought a kind of warehouse type light fixture that does 133 now, and so that's how far we've come in 9 years. Again, a sleeping trend that's about to hockey stick. Anyway, I want us to use electric vehicle battery packs as a unit at 345 volts. And I want that pretty bad. But you know, sometimes what I want, I don't get right away. And we are overrun with people who want to use the Tesla battery modules, which are much more manageable, 56-pound slab, I admit, for a 48-volt system, which most of the equipment out there uses, and all of the inexpensive solar equipment uses. There's a few problems with that whole theory. One has to do with current. We've got to do a couple hundred amps of current to do 7 or 8 kilowatts of electric power generation at 48 volts. That same amount of power at 345 volts is 23 or 24 amps. And so all our wiring and our heat issues and so forth go way down, and life gets much simpler. However, I'm being overruled by our viewership and demand for product at EVTV right now. Everybody wants our 48-volt system controller, and they want to deal with individual Tesla battery modules. So for that now, that's what we've got going on. And that takes us to the inverters and the charge controllers and so forth for 48 volts. They are seriously misapplied. And it's very simple stuff, but it's very difficult to get these people to change in the early days. Later, they will change it just fine. But right now, they're all set up for lead-acid batteries or for lithium batteries with a variety of BMS CAN communications parameters, very complicated systems, needlessly so. But the bottom line is they're accustomed to charging to 56 volts, equalizing at 60, and have a low voltage cutoff of 42 to 44 volts. That just doesn't work with Tesla batteries. In the first place, if you charge these 48 volts, you know, 2 in series, 2 in parallel is 20 kilowatt hours of 48 volts in that Tesla stack. That's great, but they're shot, completely discharged about 36 volts, and you're at the serious knee on the curve at about 38 or 39 volts. I'll put up a discharge curve for you to see here. And at 44 volts, my God, you're almost 60% state of charge. At 42 volts, you're almost 45%. And so most of this equipment's cutting off and leaving half of your capacity on the table. That doesn't work very well. And then if you use them to charge, they are wanting to, you have to make some provision to shut it off, and that often interrupts your power, and it's just a kind of a shit show of trying to get this equipment working with Tesla battery modules. It's simply not designed for the fairly unusual voltages we have, using 6 cells in series at 3.6 volts nominal. I found a group in China that makes a low-frequency transformer-based inverter for 48 volts that I really like. And we have negotiated with them to make a battery selection for their inverter that matches exactly the voltages I give them to work with a Tesla Model S battery unit. We've gotten the first ones of those in, and I am totally delighted with them. This little unit first will do 12 kilowatts continuously. It's very quiet. It has 3 fans, a great physical structure, a massive transformer. This thing weighs 165 pounds, and so it's not a lightweight Chinese inverter. This is kind of a heavy-duty unit. It'll do 12 kilowatts continuously. It'll do 36 kilowatts for 20 seconds. And between 12 and 36 kilowatts, kind of a curve based on time. You know, you can do 15 kilowatts for 5 minutes or so, or 7 minutes. That sort of thing. It has 2 modes of operation: AC priority mode and battery priority mode. Now in AC priority mode, we have a AC input, your grid, or a generator, and it just passes it through. And if you lose that grid or generator, it'll switch to battery operation within 6 to 10 milliseconds. Basically an uninterruptible power supply. I have no need of that at all, because this is kind of expensive to have batteries in an inverter whose basic job is to come on once a year when the power goes out. In battery priority mode, however, this fits in very good with selfish solar. And that is that we run from the battery, we invert it to a off-grid type output. You cannot sync this to the grid. It's an independent waveform that it puts out, and it will maintain that until the battery gets down to about 39 volts, at which point it has a little generator start relay that goes on here, and then you can use that to start a generator, or you don't need to use it at all. You can have an AC input, and an internal transfer switch simply leaves the AC not connected until you get down to the 39 volts DC, at which point it kicks in the AC. The AC then is passed through to the loads, but it also charges the battery at about 5 kilowatts, about 120 amps to charge the battery. And so in normal operation, you would work off the battery, charge the battery from solar, and use the AC output. But in the case that it got down too low, you don't need a separate charger hooked up to the grid. You can simply hook the grid into this, and it will charge the batteries and charge them back up to full, and then switch back to battery priority mode. And so that's quite a trick. So I like this. It's not UL listed or CE listed. It is UL 1741 compliant in that it has the transfer switch in it. There's no way to, if you lose the grid, to ever take power from this and put it out the grid. And so no utility maintenance people were harmed in the filming of this video. And so this is our 12 kilowatt inverter. And with all of that, 12 kilowatts of power continuous, 36 peak, tuned for the Tesla batteries, quiet and unassuming and running cool all the time, we're able to get this by buying them in quantity and bring it to you for $2,995. And that's unheard of price point with regards to that level of power in a 48 volt inverter, and there aren't any that are set up for Tesla batteries. So this is kind of it. Comes with a little device, a remote thing. Now, I've had some problems with this. It wipes out my USB port on my laptop when I'm trying to read my batteries. It's quite noisy, but it's a great little display. Shows you your load. We're at 41% now. We're in inverter mode, which means the battery inverter. No alarms, no faults. And it shows me my battery state of charge. This, of course, is our EVTV display. And we can see here, I'm at 51% state of charge, putting out 93 amps, and I'm at 43 volts. And let's see, let me get my temperature. We're at 40 degrees centigrade as our high temperature on the so what's going on here is we're putting out 94 amps from our battery, and we're powering the entire shop. We're off the grid. What we've been working on, and I'm very excited about, if you'll recall, a month or so ago, we hooked our grid-tied Solar Edge inverters to a couple of 345 volt transformer-based Chinese inverters, and actually got them to charge the batteries in reverse. I was very curious as to how that would work with a system based on 48 volts. And I understand there's a lot of things that could be done in the control electronics to kill that possibility. There's no reason for them to do it because nobody knows you can do this anyway. But we do. And so I had to get these and test them to see if how that would work. And I'm pleased to report it works alarmingly well. And we're going to demonstrate that a little bit today. On this EVTV display, the upper bar shows me negative current or discharge. The bottom bar shows me positive current or charge. and we're going to turn on our Solar Edge inverters one at a time and see what happens to our current. So let's go turn on our first Solar Edge grid-tied inverter. Okay, this is our Solar Edge 5 kilowatt grid-tied inverters. These produce the 240 volts DC, 240 volts AC from 500 volts DC on the roof. And we have 5 of them. They're each 5 kilowatts. Most afternoons we get a couple thousand watts or 2,500 watts out of them. And we're going to turn these on one at a time. Here's number 1. I set that to on, and it'll go through a power-up sequence. And then we'll have a 300-second delay, 5 minutes, while it comes up and does its connections to the internet, for one thing. It's a monitored system, and also goes through a 300-second countdown, syncs to our 60 hertz waveform. We have the grid off and are using the 12 kilowatt low frequency transformer base 48 volt inverter as our grid, if you want. And this is going to sync to it, and we got 275 seconds left until this kicks in. Okay, so here we are. We're using our 20 kilowatt 48 volt battery and our battery controller, and this is our EVTV display. We're showing 43 volts at 96 amps, a little over 4,100 watts, and we're waiting for our timeout on the Solar Edge number 1, a 5 kilowatt inverter. With today's sun, 4 o'clock, kind of sunny out, I'd say we got a shot at 2,500 or 3,000 watts. So this should cause our current to go down right smart when this kicks in here in about 15-20 seconds. We should see this 96 amp discharge from our battery drop fairly precipitously when that kicks in. Well, this is some dead air time. There it comes in, and now we have dropped at 5 minutes and 43 seconds, it looks like. Grid number 1 has synced in, and we've gone from 96 amps down to 38 amps. That's about 60 amps at 43 volts, and I would say that's about 2,500 watts. We just kicked in and should have going on there. So you can see that we're still discharging from the batteries at about 41 amps or 1,600 watts perhaps, and we're doing about 2,500 watts of our loads being handled by Solar Edge number 1. Let's go turn on Solar Edge number 2 and see what effect that has. So now I'm going to turn on number 2 of our Solar Edge grid-tied inverters and add a couple thousand watts of power from the roof to our grid-tied system. And again, about a 5-minute wake-up period to do that. Okay, we've had a little bit of cloud cover, but it's disappeared. We're at plus 12 at this point. And so our Solar Edge number 2 has apparently kicked in. And at this point, we're producing more power out of the Solar Edge than we're actually using in the shop. And without noise or any particular excitement, we've started charging the batteries. We're at 43% and we're putting 14 amps, 13 amps of energy into the battery. Now, understand that this is still making our waveform. It is what our solar edge is synced to in phase and frequency. And but while that's switching in there, we have a 48 volt primary and a 240 volt secondary on a large transformer, and then an H bridge switch that is controlled by the control circuitry. So it's working to invert, but there's more power, a higher voltage on our system, then this is regulating the voltage to in the inverter, and that's forcing energy back into the battery. A little cloud cover comes over, and so we're at 26 amps discharge now in the face of the clouds, and as they dissipate, and so it'll go back and forth dynamically between charging and discharging as the overcast haze waxes and wanes over our solar panels. This is actually kind of delightful for me to watch because of what it means. We're charging or discharging our batteries dynamically during the day depending on the cloud cover. And so when we're not producing enough, we take it out of the batteries, and when we're producing too much, with our solar edge grid ties, we're putting it into the batteries as charge, and our inverter isn't making anything. By the way, the inverter can't tell whether it's charging or discharging in this case. So it presents a percentage of load either way. And I've had this up to 230 amps of charge, 13.5 kilowatts of charging power coming in through the inverter into the batteries, and it's a 12 kilowatt inverter, and it did it for 40 minutes. I finally had to shut it down because the battery was too full. The bad news on this kind of system is you cannot really let the grid-tied inverters to continue to run after your battery is full, because you'll overcharge the battery or disconnect it. If you disconnect it, your inverter goes down, the grid-tied inverters go down. Possible damage to the equipment, it's kind of a disaster. So one of the things we're going to do is take our charge enable output of our battery controller and use it to control a contactor connecting the grid-tied inverters to the system, much as we did with the MPPT charge controllers, and kind of for the same reasons. And so right now, even with two of them up, we're using 44 amps out of the system because of the overcast haze. Let's go turn on number 3 and see what effect that has. Back at our grid-tied inverters, let's turn on grid-tied inverter number 3, and that'll bring up another 2,500 watts or so of solar, 240 volts AC. Again, this produces a little bit higher voltage than what it's reading on the grid, or in this case, our 12 kilowatt off-grid inverter. And so if it produces more than our loads, that will force energy into the battery. Normally we wouldn't do that into the grid, but in this case into the battery. And if it doesn't, it will kind of match the voltage of the output of that inverter and provide for our loads. If our loads require more than these put out, the inverter will maintain the 240 volts AC by drawing energy from the battery. Okay, we've not only lifted a lot of our cloud cover, but kicked in. We're in a solar number 3, and so we're showing 49 amps of charging into the battery at 43.7 volts, and 42% state of charge. And so, again, we're waxing and waning with the sunlight, but showing a fairly steady 49 amps right now as our Solar Edge number 3 has come online, and we're 3 of those. We were doing about 4,100 watts of consumption in the shop, and now we're at a 48, 49 amps at 43. That's about 2,000 watts into the battery. And so our 3 units out there are generating about 63 or 6,500 watts total, and 2,500 watts are going, or 2,000 watts are going into our battery. Carry this to an extreme, and we will fire up number 4 and see what happens. We're back at our Solar Edge grid-tied inverters, and in this case, we're going to turn on number 4 and bring that up, and that should add another couple thousand watts to our total. And we take a look at the inverter and see what happens to our current flow, whether it be in or out of the battery. Okay, we're at about 36 or 37 amps, waiting for number 4 to come up, I believe. And I'm going to shoot you a little video of the EVTV so we can actually see this take place, a little bit of a close-up. And we're at 40 amps, pretty good sun out, with 3 of them running. And we should come up on number 4, come online here in a few seconds. That's about 5 minutes there. It's about 5 minutes and 10 or 15 seconds to bring it up. So let's see if we can catch it here. And there it goes. And number 4 has come up. We're now shooting 87 amps into the device, into the batteries. 101 amps. And I can hear our fans coming up, but note this thing has been strangely silent. It just doesn't whimper at all, but at this point we're doing at 100 amps about a 35% load. It thinks it's making about 4,000 amps or 4,000 watts of power, and we've just brought up maybe our DC fan a little louder. It has 2 in the front for the transformer and 1 here, and they are kind of controlled by temperature, and so that's working pretty good. And I'm at 99 amps, and that's at 44 volts is 4,400 watts. Our shop's doing about 4,200. So I'm doing about 8,000 watts on 4 Solar Edge grid ties. They're operating the entire shop and generating 4,000 watts of charge into our battery, which is now at 44%. Let's go fire up number 5 and see what happens. We're back at our grid-tied inverters, the Solar Edges. I'm going to turn on number 5. Again, 300-second time delay, and we will bring that back up on our system and see what effect that has on our 12 kilowatt 48 volt inverter and battery system. I'm going to put up a diagram here while we're waiting for number 5 to time out. Is that it? And so I'm going to put up a diagram of what we're doing here. This is an AC coupled 48 volt battery system, and you can see what I'm using here in the diagram is the microinverters that go with the panels. Eventually we're going to do another array on the roof, again, of our Panasonic HIT panels. I really like those. They use kind of a hybrid technology that Solar City was trying to develop and kind of failed. And Panasonic has partnered with Solar City now on their Buffalo, New York plant, and are going to be making Panasonic panels kind of under Solar City. But they're about 19.6% efficient, but they're a 96 cell panel, and so they're a little higher voltage. Enphase has just now, this supposed to be out this past month, I still can't get any, come out with an IP7 version, and they call it an IP7X, specifically designed for the 96 cell Panasonic panel. Our next phase is to see if we work with micro inverters as well as we do the Solar Edge. Since they work the same way, I simply don't expect any difference. But one of the things that gets you guys in trouble is you type yourself smart. It makes sense that it would work, but we won't know until we hook it up and test it. There isn't a shortcut to knowledge on this stuff, and one of the horrifying things that happens in technology with this internet is you have this huge amount of tribal lore being passed around without anybody doing any testing of it or any first order determination of how it really works. I've been told completely that what we're doing right here, right now, will not work. And in fact, the company that makes this device told me it had no possibility of working this way. Well, right now, I've got their undivided attention because it is working that way and working very well. And so their product is capable of something they didn't even know it would do. Off of their AC input, they can charge at about 5 kilowatts. I've had this at 13.5 kilowatts running off of grid-tied inverters that are synced to the output of this inverter. And we are kicked in now. We're showing 133 amps. This is crazy. 130 amps at 44 volts. James is our intern. He can work that out for me. 131 amps and 44.6 volts. 5,798. And that's what we're doing right now off of our 5 Solar Edge grid-tied inverters. But I've done over 230 amps using the same inverters, and with a similar shop load on it, simply better sun. It's 4:45 in the evening here right now, and at 1 o'clock in the afternoon, it's smoking around here as far as solar goes. And so we've done this at up to 230 amps. I think the hive hits 280, but we did 230 for about 40 minutes and simply filled up our batteries, so we had to shut it down. Everything was running. The battery terminals were getting warm. I'm setting the temperature cutoff at 55 C. Right now we're at 39, so not a big deal. But if you run it for an hour or two at 100 or so amps, that temperature starts to crawl up. We're going to do a big project at once this testing is completed on all the parameters of our 12 kilowatt inverter. I've had several inquiries from Puerto Rico and Costa Rica, and they're not too concerned about UL listings. And we're going to get a large Wigman 72-inch cabinet, put 16 Tesla battery modules in it. This inverter, a contactor to shut off our grid tied, and you bring your grid right down into the enclosure, and your grid into the enclosure, but your grid tied photovoltaics right into the enclosure, and then you'll have an output to your loads panel in your house. And so what we get this down to is our battery controller, the Tesla batteries in an inverter. That's pretty much, and one contactor, that's the whole deal to take a grid-tied solar system and convert it into selfish solar that only uses the grid when you just ran out of sunshine and battery, or as we say, airspeed, altitude, and ideas all at the same time. And at that point, it'll feed from the grid or a generator, which you can fire up. And in many areas of the world, that's actually more appropriate. And it should be rare enough a situation that a generator would be appropriate. And we actually have a relay output to start the generator when the battery gets down to the low voltage battery alarm, which we've measured at about 39 volts. And so that's what's going on with this inverter. We're going to do a project with a big enclosure. As I say, an 85 kilowatt battery, about an 80 kilowatt, I guess, hour battery, 16 Model S modules, this inverter, and probably cool it because who knows how big a solar system they'll want to tie that into. But kind of the mother of all 48 volt Tesla-based solar systems. And the key feature of it, you can still do DC coupling. You simply take charge controllers, run your photovoltaics to the battery terminals. But this is kind of cool because you can go to the micro inverters and bring 240 down from the roof and tie it right into your box through a contactor so we can shut it off and actually charge your batteries and feed your loads in an AC coupled fashion. And nobody knew you could do this, but it works. We're not guessing at this point. We've done it every day this week, and so far, no fatalities. So put your life alerts on stun and cinch up your depends, old guys. We're going in. Stay with us.